Hello everyone, welcome to lecture 6 and module 5. We have covered the half length of this course. Today will be the last lecture of week 6. After the 10th week, we will have practical session in the 11th week and the 12th week by the Dr. Sandan Ghosh. So today we will start with another porosity logging tool which is called the Neutron porosity logging tool. So we have covered a number of logs starting from the mud log, SP log, RISTI log, and then we discussed the density porosity logging tool. After density porosity logging tool, now we will cover the neutron porosity logging tool. After neutron porosity, we will cover the sonic or acoustic logging tool. Then we would have covered all the basic measurement which is present in the routine wireline logging operations. So let's start today's lecture. Today's lecture is about the neutron porosity logging tool. So today we will discuss about first little bit of the chemistry or little bit of knowledge about the neutron, such as how the neutrons are classified, at least in our wireline logging operations, and how this neutron can interact with our formation material. Also different application of neutron logging tool, and then we will discuss the how this neutron logging tool works, what is its principal measurement. So tool data, like in the case of density logging tool, was bulk density of the formation. Similarly, in case of neutron porosity logging tool, it also does not measure the porosity directly. The principal measurement or the main measurement of the tool data is our hydrogen index of formation, and hydrogen index can be converted to porosity. So porosity, just like in density logging tool, is inferred from the tool data. We will also discuss different types of tools, neutron logging tools, and how they differ from each other, and what are the advantages or disadvantages of using different types of neutron logging tools. So this will give you a very good idea about how the neutron log is affected by the wellbore environment and how the neutron log data can be interpreted in terms of our formation porosity. So let us start with the neutron logging application first. So neutron logging tool can be used for porosity determination, the identification of gas bearing formation, sand boundary identification, and also it can be used for formation elemental and the mineral identification. That means we can determine the individual element concentration or individual mineral concentration inside the formation. It can be used for the reservoir fluid saturation, and thus by monitoring the fluid saturation changes inside the reservoir, we can use the neutron logging tool for reservoir monitoring operations, such as the monitoring of our different development and production activities. So these are the general application of neutron logging tool. But in this course, we are only interested in the neutron porosity logging tool. That means the application of neutron logging in the estimation of formation porosity. So the tool that we are going to discuss, the tool that we will be discussing or using in this course or in this lecture will be focused on determining the porosity of the formation and not on the different properties such as reservoir fluid saturation measurement or the formation elemental and mineral identification at elemental level. So the porosity logging tool or the neutron porosity logging tool can determine the porosity of the formation. It can also identify the lithology. Basically, it can differentiate between the scaly formation and non-scaly formation. So shell or pure shell can be easily identified along with the density log. If density log data and the neutron logging data is plotted against each other, we can easily identify where we have pure shell and where we have our reservoir rock formation. So that's why we can use in the differentiation of our porous formation or reservoir formation from non-porous formation. Similarly, we can use it to detect the gas bearing zone. So gas bearing zone can easily be identified if you use the data along with the density log data. So when density log data and the neutron logging data are plotted against each other, a separation exists between the density data and the neutron data. So by identifying this separation, we can know where the gas bearing formation exists. And we can also estimate the cell content. So as we have already discussed, SP log can be used for the cell content determination. The gamma ray log, which is the primary shell indicator or cell content estimated tool, can also be used. So gamma ray log can also be used, but in many cases the reading from the gamma ray log may not be reliable, or the calculated cell content from the gamma ray log may not be good enough. So different conditions inside the reservoir might prevent the use of gamma ray log. In that case, density and neutron log can be used together to give us an idea about the silliness of the formation. So after the gamma ray logging tool, probably the neutron and density log combination is one of the best method available to calculate the shell content of the formation. So these are the applications that we'll be focusing in this course. So this is an example of our neutron logging tool data. So we have gamma ray here and we have neutron porosity here. Like in density log, the density or the bulk density was plotted. As I mentioned in the start, neutron logging tool, the primary tool measurement is the hydrogen index, but generally the neutron log is printed the converted porosities. That means whatever the tool is measuring inside the wellbore, hydrogen index, it is converted to neutron porosity reading, and that neutron porosity reading is presented along with the our other logs. Another example of neutron log here. This is the data that we'll be using in the practical session. So you will be working on this data. A demonstration will be made for this data to how to interpret in terms of our reservoir rock and fluid properties. So in this data we have in the first track, as I mentioned earlier, we generally have the borehole size, that is bit diameter size, and the caliper size, and then the gamma ray curve. So all these three curves are present. Then we have the formation restituted data on the second track, and thereafter in the third track we have always the porosity data or the porosity logging tool data. So here we have both, you can see here density and the neutron. The red one is our density log data, the red curve, and the green curve is our neutron logging tool data. And in the last track we have our acoustic logging tool or the sonic logging tool data. So here you can see when the density and the neutrons are plotted against each other, you can see there is always some separation behind these two data. So somewhere density log data is reading high porosity, somewhere neutron logging tool data is reading high porosity. So by observing this separation between density and neutron logging tool, we can get an idea about whether we have a gas or we have a shell. For example, here at the top, if you can see, gamma ray reads very high. So this is probably a shell, pure shell, and you can see here density data and the neutron data, they are separating from each other. So generally in against shelly formation, neutron logs will read high porosity. As you can see, neutron porosity reading is increasing in this direction, and density logging tool data will be reading low porosity. So we will discuss this, how to plot these two data together and how to identify gas or shell. Now let us discuss the different types of neutron on the neutron source which we use in the neutron logging tool. So in density logging tool, we were bombarding the formation with the gamma ray. Here in the neutron logging tool, we will be bombarding the formation with the neutron. So the tool is going to emit a high energy neutron with energy level around 4.5 mega electron volt. So generally we use different radioactive sources such as radium, plutonium or americium, and along with that we use also the beryllium 9. These three sources can be used for generation of an alpha particle, and when that alpha particle is reacted with the beryllium 9, it will give rise to a neutron. So this way these two radioactive sources can be used to generate the neutron which will be bombarded inside the formation. So what type of neutron we have? So neutron can be classified as fast neutron, intermediate neutron, slow neutron, and slow neutron can further be classified into epithermal and thermal neutron. So if a neutron have energy greater than 100 kilo electron volt, it is termed as fast neutron. Intermediate neutron have energy around from 100 electron volt to 100 kilo electron volt. And epithermal neutron, they have energy around 0.1 electron volt to 100 electron volt. Whereas the thermal neutrons, they have energy 0.025 electron volt or less. So it is the fast neutron which are emitted from the neutron logging tool. The source is going to emit the fast neutron because they have the energy level around 4.5 mega electron volt. When these neutrons go inside the formation, they will interact with the formation and then come back to the tool where they are recorded at a detector. So by knowing the count rate at the detector, we can get an idea about our formation porosity. So let us first discuss what type of interactions are possible inside the formation. So when neutrons are emitted, they are going to collide with the nucleus of different atoms present inside the formation. So a formation can have a number of nucleus of different element. For example, you can have carbon, oxygen, calcium in a carbonate formation, and in a sandstone formation you will have silica and oxygen, and in the hydrocarbon, when the hydrocarbon are present, we will have carbon and hydrogen, and if water is present, then again we will have hydrogen and oxygen. So emitted neutron or the bombarded neutron inside the formation, they will collide with the nucleus of these atom. So three types of interactions are possible, or the three type of interaction that we are interested in neutron logging application. So first is our elastic scattering, second is inelastic scattering, and third is capture. This is elastic, this is inelastic interaction, and third is our capture interaction. So what we need to keep in mind that where a gamma ray is emitted. So in inelastic scattering we have a gamma ray emission, and in a capture interaction we also have a gamma ray emission. So as I mentioned in the start, neutron logging tool can be used for formation water saturation determination. There we also interested in the our inelastic scattering. We tend to investigate the our inelastic scattering to get an idea about what is the formation water saturation. Generally the log is called carbon oxygen log. So carbon oxygen log can be used for formation water saturation determination. So if you are interested about how water saturation can be measured, you can refer to different books to get an idea about this carbon oxygen log. Once again, we will be only interested in the our porosity determination from the neutron logging tool. So in elastic scattering, what happens? This neutron is going to collide with the nucleus. After that, the neutron will travel its separate path, nucleus will travel in a separate path. So total kinetic energy remains same in this collision. That means when neutron collide with the nucleus, it will transfer some of its energy to the nucleus, and the kinetic energy of the nucleus will increase and the kinetic energy of the neutron will decrease. So in elastic scattering, no gamma ray emission is taking place. Kinetic energy, total kinetic energy before the collision and after the collision remain same. There is no loss of energy or energy transfer anywhere. But in inelastic scattering, what happens is that when a neutron collides with the nucleus, the total kinetic energy before and after are not the same. That means some part of the kinetic energy of the neutron is transferred to the nucleus. So energy of the nucleus is increased, it will go to a higher energy state or in an excited state where it will be unstable. So to remain stable, it will go back to the our ground state by releasing a gamma ray. So in elastic scattering, a gamma ray is emitted. Why? Because when the neutron collide with the nucleus, it is transferring some of the energy to the nucleus, which is exciting our nucleus, and to remain stable, it is again coming back to the ground state and it releases a gamma ray. Again, inelastic scattering will depend upon the threshold energy level. That means every nucleus has certain excitation energy. That means if the energy of our incoming neutron is less than this excitation energy, no inelastic scattering can take place. Only elastic scattering or maybe the capture interaction will take place. So energy of incoming neutron must be greater than the our excitation energy of our nucleus. Now this gamma ray which is emitted after the inelastic scattering, the energy of this gamma ray is related to the what type of nucleus it is. That means different nucleus will emit gamma ray of different energy. So by monitoring the gamma ray energy and the gamma ray count, we can get an idea about what type of elements or nucleus are present inside the formation, which is used in our mineral identification. So nowadays modern neutron logging tools are also used, which can give you an idea about our formation mineralogy. But generally they are not routine. Our routine wildlife logging tools are our SP, gamma, caliper, density porosity, neutron porosity, and sonic porosity, and the Rayleigh logging tool. But nonetheless, we can use the tool which can monitor our inelastic scattering to give you an idea about elemental composition of the formation. The third type of interaction is our capture interaction, where the energy of neutron is so low that when it collides with the nucleus, nucleus will absorb it. So the neutron will collide with the nucleus and The neutron will be absorbed by the nucleus. Nucleus will produce next isotope of higher mass, which will again come back to the original or stable isotope by de-exciting and releasing a gamma ray. So a gamma ray will be also emitted in the capturing interaction, and this will be called our capture gamma ray. Whereas this gamma ray, which is emitted in the inelastic scattering, that is called our inelastic gamma ray. So these are our nucleus and neutron interaction which is possible in our formation. Now, if you look at this figure, we have two types of interaction. First case, a neutron is colliding with the nucleus. Second case, also neutron is colliding with the nucleus, but here the nucleus mass is very low. Here the nucleus mass is very high. That means size of nucleus and neutrons are different. In this case, nucleus and neutron almost have same size or same mass, but in this case, neutron and nucleus have different size or different mass. In first case, what happens when the neutron is colliding with the nucleus? Neutron velocity is decreased. But in the second case, what you can see, the neutron is colliding with the nucleus. Neutron velocity is almost same. There is no change in the kinetic energy of the nucleus. In the first case, nucleus kinetic energy is increased and the neutron kinetic energy decreased. But in the second case, neutron kinetic energy remain constant and the nucleus kinetic energy also remain constant. So we can understand this interaction in this way. For example, let us take a very small ball and try to throw this small ball towards a very heavy or very big object. You will see that ball will come back towards you and the heavier object, big object will not move at all. But if we take the smaller ball, throw it toward a very smaller object, we will see that the smaller object will move. Some part of the kinetic energy of the ball that you are throwing will be transferred to that smaller object. That's why in the first case, when the size of nucleus was small, the kinetic energy of the neutron was decreasing and the kinetic energy of the nucleus was increasing. But in the second case, the kinetic energy of the nucleus will remain constant. So this also happen in our radioactive rock formation. So when the neutrons are bombarded, it will lose most of its energy when it will collide with a nucleus of same size. So smallest nucleus is our hydrogen. So when neutron is colliding with the hydrogen nucleus, it is going to lose the maximum energy. That's why, as I said in the start, neutron logging tool primary measurement is the hydrogen index. That means the neutron energy decrease when the neutrons are colliding with the formation. It will be mainly depending upon the hydrogen content of the formation. So if I have more hydrogen inside the formation, there will be a large probability of the collision of neutron with the hydrogen. Thus, neutron will lose its energy at a faster rate, because when the neutron is colliding with the hydrogen, it is losing its energy at a faster rate because size of neutron and size of nucleus are almost similar to each other. So whenever a neutron collides with the nucleus of hydrogen, it is going to lose the maximum energy. That's why if you have more hydrogen content, then the fast neutrons will be converted to epithermal, then thermal neutron at a faster rate. If you have less hydrogen content, then the fast neutron will be converted to epithermal and thermal neutron at a lower rate. So let us discuss how the tool works. Now we have understood what type of interaction are possible. So as I mentioned in the start, it is a porosity law, that is hydrogen content measurement or hydrogen index measurement. So the tool is going to record the hydrogen content, not the porosity. So always keep in mind what is my tool is recording and what do I want as an output. As an output, I want the porosity, both in case of density lock and in case of neutron lock. So you must understand what is my primary tool measurement and how it is affected by the Borel environment, so that you can correct the tool response or use only the data of good quality for interpretation of porosity. So sometimes what can happen is that the tool measurement might not be representative of our formation. So if you use the same data which is of bad quality and interpret the porosity, it will give you a wrong porosity. For example, as we have discussed in the our density log, that mud cake compensation or the mud cake correction is very important. That's why the delta rho or the correction values are also presented along with the bulk density data. So delta rho can be used as a qualitative measure to know whether the bulk density data recorded by the tool is of good quality or not. So whether we should use the bulk density data or the bulk density of the formation to calculate the porosity or not may be defined by the or controlled by the our delta rho correction values. That's why it is always important to remember that what is my tool primary measurement. My tool primary measurement is not the porosity. My tool primary measurement is the hydrogen content. So whether this hydrogen content is liable or not, that should be first established before calculating or inferring the porosity values from the our hydrogen index measurement. So the tool have a source which is emitting fast neutron. The fast neutron are colliding with the formation nucleus. So after the collision, the neutrons are going to lose its energy. So they will be converted to epithermal neutron. Then again they will go more number of collision. Then they will be converted to thermal neutron, and they will have more number of collision. Then they will be captured by the formation nucleus, and a capture gamma ray will be emitted. So the tool can either record as these two detectors, either the thermal neutron or the capture gamma ray or the epithermal neutron. So during this course of the travel of the neutron inside the formation, we are emitting the fast neutron. The fast neutron are converted to epithermal neutron upon collision with the nucleus. Epithermal are converted to thermal, and then thermal neutron are getting captured, which give us the capture gamma ray. So depending upon the type of tool, we may have different type of detector. We may have the capture gamma ray detector, or a thermal neutron detector, or an epithermal neutron detector. So as I mentioned earlier, the neutron is going to lose its energy at a very fast rate when the hydrogen is present inside the formation. So when the hydrogen is present, it is having the same size. That's why the neutron upon collision will lose its energy at a faster rate. So if we monitor the how many thermal neutrons are reaching the detector, or how much capture gamma ray are reaching the detector. So it will depend upon the hydrogen content of the formation, because hydrogen is controlling at what rate the fast neutron can be converted to our thermal neutron, which will control how much capture gamma ray will be emitted. So in neutron logging tool, if you compare these two figure, one is having a high hydrogen content, second is having low hydrogen content. So in first case, when we have high hydrogen content, what will happen is that we have a large number of hydrogen. So neutron will collide with the hydrogen nucleus. They will get slowed very rapidly. So conversion of fast neutron to our epithermal neutron or thermal neutron will be at a very fast rate, because we have more hydrogen content. So more number of collision with the hydrogen atom. So more the energy decrease of the bombarded neutron. So since the fast neutron are converted to thermal neutron much closer to the source because of high collision with the hydrogen atom, so all the thermal neutron and the capture gamma ray will be emitted near the source. That means thermal neutron will be generated near the source, and when the thermal neutron are captured to release the capture gamma ray, the capture gamma ray will be also released near the source. So at the detector, we will have very little radiation. That means thermal neutron count rate and the capture gamma ray count rate will be very, very low. So most of the count rate of thermal neutron or the capture gamma ray or epithermal neutron will be observed near to the source, not near the detector. Whereas if you have low hydrogen content, what will happen? The conversion of fast neutron to epithermal, then the thermal neutron, will happen at a slower rate because we have less amount of hydrogen. So collision of fast neutron with the hydrogen is less. So neutrons are going to lose energy at a very slow rate. That's why before converting to thermal neutron and releasing the capture gamma ray, the neutron will travel a very far distance inside the formation. That's why we will have very good count rate of thermal neutron and the capture gamma ray at the detector. So a high hydrogen content will give us the low count rate, a low hydrogen content will give us the high count rate at the detector. Since the count rate is directly proportional to what? Our hydrogen index or the amount of hydrogen inside the formation. So a high count rate is related to what? Low hydrogen content, whereas a low count rate is related to what? High hydrogen content. So this way, count rate is related to our hydrogen content of the formation. Now, how this hydrogen content is related to porosity? So hydrogen concentration is dependent on the porosity, because the matrix, the solid part, whether we have sandstone or carbonate rock, they usually do not have any hydrogen. So only hydrogen it comes from the fluid. That means our water also have hydrogen, our hydrocarbon also have hydrogen. The amount of fluid is responsible for the hydrogen content. If you have more amount of fluid, whether water or hydrocarbon, will have more amount of hydrogen content. Since the fluid part is stored in the porosity of the formation, so if we have high porosity, that means we have more amount of fluid, that means we have more amount of hydrogen concentration or our hydrogen index. We have already discussed that counter rate is inversely proportional to our hydrogen concentration. When we have low hydrogen content or hydrogen concentration, we are getting what? High count rate. So we can also write now count rate is inversely proportional to porosity. If I have high porosity, that means high hydrogen concentration, that means our low count rate at the detector. This way the count rate is related to our porosity of the formation. Now, before we go on to the our porosity calculations and other things, let us first discuss the how different interactions are monitored or presented. So we are going to use microscopic cross section. So a microscopic cross section is nothing but it is a measure of the probability of different nuclear reaction between a neutron and the any individual particle, maybe neutron and a nucleus in our case. So this cross section is interpreted in terms of effective target area that a nucleus interact with an incident neutron. For example, let's say I have taken a general example. For example, let's say I have a very big area. If I throw something on it, the larger the surface area, the greater is the probability that whatever I am throwing on this surface area will collide with this surface area. So if I am throwing a particle on this surface area, the probability of the collision will be high if this surface area is very, very large. So the same concept can be applied in our nuclear interaction. So how much target area a nucleus is presenting to an incident neutron, it will define the probability of collision. So this way, this cross section is defined and calculated to give you an idea about the probability of that a neutron will collide with our nucleus. So this macroscopic cross section can be measured. We already have a database of different element. We know that what are the macroscopic cross section of different interaction. For example, if you see in this table, we have two cross section. One is the capture cross section and second is our slowing cross section. So slowing cross section is nothing but the probability that a neutron will collide with the nucleus and it will get slowed. That means the ability of our formation element nucleus to slow the neutron. Where the capture cross section is nothing but is the ability of our formation element nucleus to capture the neutron. So it is nothing but the probability that a neutron will get captured by our nucleus. So I can say that if an element nucleus have higher slowing cross section, it is going to slow the neutron at a faster rate. If an element having low cross section, low slowing cross section, it is going to slow the neutron at a slow rate. Similarly for the capture cross section also. So if an element nucleus have very high capture cross section, it can absorb the thermal neutron at a very rapid rate. Whereas if an element have very low capture cross section, it is going to absorb the neutron at a very slow rate. So you can see in this figure, the slowing cross section is highest for hydrogen. As we have already discussed, you can see hydrogen have around 20. Rest have low cross section compared to our hydrogen. How much collision does it take place by neutron with the nucleus to convert to thermal neutron? 80 number of collision. So 80 number of collisions are required by a fast neutron with the hydrogen atom to be converted to our thermal neutron where they can get captured. Rest of the element have very, very high values. So hydrogen can slow down the neutron at a faster rate. All the other elements, whether carbon, oxygen, calcium, chlorine, potassium, which are present inside the formation, they have very low slowing cross section. That's why our count rate is related to our hydrogen index or hydrogen concentration of formation. So if I talk about now capture cross section, so you can see the cadmium and boron and then chlorine have the highest capture cross section. So cadmium have around 2500, boron have around 700. That means cadmium and boron can capture the thermal neutron at a very fast rate. So generally cadmium and boron, these rare earth element, might be present inside the Selly formation in a trace quantities. So even in trace quantities, they can absorb the thermal neutron at a very rapid rate because they have very high capture cross section or very high ability to capture the thermal neutron. The element which is generally present inside the formation is chlorine in the formation water. So if we have a saline formation water, the chlorine will be present, and the chlorine have a very high capability to capture the thermal neutron. So whenever chlorine is present in saline formation water, it is going to destroy the our thermal neutron population. So we have to keep in mind that which type of detector we are using, whether we are going to detect the thermal neutron or the capture gamma ray or the epithermal neutron. So accordingly, all these will be affected by the type of element present inside the formation, its flowing cross section as well as the capture cross section. So as you can see that although hydrogen slowing cross section is very high, but other elements do have certain amount of slowing cross section values. That means tool is going to respond to all the elements present inside the formation. The value of slowing cross section for other elements are not zero. Only thing is that the value of slowing cross section for hydrogen is very high. It is such that the main response is going to come from the our hydrogen. But nonetheless, when we are converting the tool data to porosity values, we need to keep in mind that the tool data is responding to all the other formation elements so that we can convert the hydrogen index to our porosity values by knowing the individual contribution of each other element or each other mineral inside the formation. So the metric response to slowness of the neutron or slowing cross section of matrix must be known to us. The slowing cross section of fluid must be known to us so that we can convert the hydrogen index to porosity values. Now, another thing that we need to keep in mind that the concentration versus cross section. That means if an element have very low, let's say capture cross section, it have very low capture cross section. But if it is present in the very large quantity, it can absorb the thermal neutron because it have very high concentration. Second case, if an element having low concentration but very high capture cross section. So even a low concentration of an element which have very high capture cross section can absorb the our thermal neutron. For like cadmium have very high capture cross section. Even if it is present in the low concentration, it can destroy the thermal neutron population by absorbing the thermal neutron at a very rapid rate. So sometimes our neutron logging tool data might be affected by the presence of all these elements even if these are present in the trace quantities. That's why if you remember that I have already mentioned many times that we generally record two porosity logs such as density neutron or density sonic or neutron sonic we can record, and we never interpret the log without information from other log. That means all the logs should be taken together to get an interpretation of our well login data. So in case let's say when the cadmium and boron is present, if I convert the neutron log reading to porosity values, I will have a large amount of error if I don't account for the presence of cadmium and boron. But if I compare the neutron log data along with the density log data or any other log data, I can detect the presence of these rare earth element and can find out what is the effect of all these elements on my neutron porosity logging tool. So that whatever the calculated porosity that I am going to get from density data or the neutron data is correct and it is true porosity of the formation. So today we discuss the basic principle of neutron logging tool. What are the different type of neutron, how the neutron interact inside the formation, and how this interaction is related to our hydrogen index and how hydrogen index is related to porosity. So neutron logging tool, it is going to measure the hydrogen index or the tool data, that is the count rate, either thermal neutron or the capture gamma ray or epithermal neutron can be converted to hydrogen index, and then hydrogen index can be converted to porosity values. In the next class, we will discuss how to calculate the porosity from neutron logging tool. So see you in the next class.